All right, we'll get back to section 4.7 now. And we're on problem 6 on this worksheet here, talking about optimization problems. And so let's take a look at this one. Find the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius 4. Okay, so I've drawn a circle of radius 4, and I've put an isosceles triangle in the circle. Of course, an isosceles triangle would be where two legs of the triangle are going to be the same measure. Okay, let's I guess in this picture, I have dropped a perpendicular down, and I'm going to call the distance from the center of the circle to the bottom of the triangle x, and then the distance from the center of the bottom of the triangle over to one corner of the triangle y. Okay, and you'll notice that I've created a smaller right triangle here. The hypotenuse of the right triangle is 4. Okay, now what are the dimensions of the isosceles triangle of largest area that can be inscribed in a circle of radius 4? More specifically, like what is the base and the height in this triangle? Okay, how should the triangle look so that it is as big as it can possibly be? Well, since I'm working with area of a triangle, area of any triangle is 1/2 base times height. So I've got 1/2, the base would be 2y. Again, y is just the distance from the center over to one corner of the triangle. 2y would be the base of the triangle then, okay? And times the height, so x plus 4 would give me the height of the triangle. The 2's would cancel, and I'm looking at y times x plus 4. Okay, now I'm going to maximize that area. I want to find the largest area of this triangle. Okay, and I'll need to know what this looks like then in terms of just x. Well, I've got this smaller right triangle built in, and the fact that that's a right triangle means that I can use the Pythagorean theorem. X squared plus y squared equal 4 squared is 16. And if I solve this for y, subtract x squared and take the square root of both sides, then y would be plus or minus the square root of 16 minus x squared. Okay, now y negative means that the triangle would be just flipped about the vertical axis. So because you'd be drawing the same triangle flipped about the vertical axis, it's enough to just disregard the plus minus there that comes up. Okay, and so the area then, y times x plus 4, would be the square root of 16 minus x squared times x plus 4. That way this function is all in terms of x. Now what is the conditions on x? Well, you're working with a circle of radius 4, right? So x can't be bigger than 4, otherwise you're outside of the circle. Now x could be a negative. X negative just means that the base of the triangle would be above the center point. Okay, x positive means that it would be below the center point. So if x was a negative, I'd be drawing a triangle, kind of like that. Now I'm looking for the biggest possible triangle. So I think just, an observation, if I were to draw a triangle that is as big as it could possibly be in the circle of radius 4, I think I would want the base to be below the center point. Okay, because it would take up more space in the circle. But remember, a strategy that we're trying to do here is we're trying to get a closed interval. Okay, so it is possible that x could be negative 4. Okay, if x is negative 4, then you would just have a single point up at the top of this circle, and you're not actually building a triangle. So the area would be 0, if you just have a single point. If x is 4, you would just have a line in the circle, a vertical line here. And again, that would produce an area of 0, okay? So we wouldn't be, considering those, although those numbers give us a closed interval here. So I'd want to use those endpoints. That way I can move forward by using the techniques that are in section 4.1 rather than for 3 here with the first derivative test or a second derivative test. Okay. So in 4.1, if you have a continuous function on a closed interval, you're guaranteed to have both an absolute max and an absolute min. We care about the absolute max. We're maximizing the area. And so let's go ahead and get our critical numbers and plug those numbers into the function along with the endpoints and see which one is the biggest. Okay, so I'm going to do that. I need a prime of x, that would be a product rule. So the first is x plus 4 times the derivative of the second, that'd be 1/2 times 16 minus x squared to the negative 1/2 times negative 2x. The 2's would cancel, and that would leave you with negative x divided by the square root of 16 minus x squared if you were to write that in radical form. Okay, so I got first times derivative of the second plus the second times the derivative of the first, derivative of x plus 4 is 1. Okay, and I want to simplify this. I'm going to get a single fraction. The square root of 16 minus x squared times the square root of 16 minus x squared, that's 16 minus x squared. Okay, and I've also distributed the negative x into these two terms. And then combine your like terms. Okay, so you're looking at negative 2x squared minus 4x plus 16 in the numerator. If you multiply both sides of this equation, now once you set it equal to 0, multiply both sides by the denominator, then that'll clear out the fractional form that we see on the left. And so we've got negative 2x squared minus 4x plus 16 equals 0. You can make the numbers a bit nicer by dividing both sides by negative 2. So I've done that, and then this quadratic equation is going to factor nicely for us as x plus 4 times x minus 2. So x equal negative 4 or x equal 2 would be the two critical numbers. Now, in using the extreme value theorem, I'm going to be plugging in the endpoints on this interval anyway, so I would have plugged in negative 4, regardless. 2 and negative 4, though, are critical numbers. So let's go ahead and plug them into A and see what has the biggest output. Well, if x is 2, you're going to have 6 times root 12, or that would be, square root of 12 is 2 root 3, right? So 6 times 2 root 3 would be 12 root 3. And if you plug in negative 4 into the function, you're going to get 0. And that would make sense, right? Because if x was negative 4, I mentioned earlier, you'll just have a point at the top of the circle. You're not actually building a triangle. So the area of that triangle would be 0, right? If x is 4, then 4 squared is 16. 16 minus 16 is 0. 0 times any number is 0. And again, if x is 4, you're not actually building a triangle. You've just got a line through the center of the circle there, and so the area would be 0. Okay, this value produced the biggest output when x was 2, so that is the proof showing that x equal 2 creates an absolute max on the graph. Now we want to know the dimensions of the triangle, so if x is 2, then let's see, the height would be 4 plus 2 is 6. Okay, and then the base, if x is 4, if x is 2, 2 squared is 4, you're going to have root 12, but then 2y gives us the distance all the way across the base, right? That was this here. So 2 times root 12 would be 4 root 3 then if you simplify. Okay, and these dimensions would produce the biggest triangle. Problem 7 is kind of similar, only it's a 3D situation rather than a 2D. Going to be kind of similar, though, to what you saw in problem 6. In this problem, we want to find the volume of the largest circular cone that can be inscribed in a sphere of radius r. Okay, so I've drawn a picture of a sphere of radius r, and I've also drawn a cone in the sphere. And I want to find the biggest possible cone that can fit in this sphere of radius r. Now, r is a number, of course, r has to be positive, right? But they're not giving me a number like they did in the last problem where, like r was 4 in this last problem. That's okay. So I'm going to be building just a general formula here that would allow me to get the largest cone fit into a sphere of radius r. There's going to be several problems like that in the homework. You'll notice that you'll be kind of just creating a general formula. Okay, and all right, now the volume of any cone is 1/3 times the radius of the circular base, 1/3 times pi times the radius squared of the circular base times the height. Okay, and now in this picture, I got this cone, like I said. The radius of the sphere is r units, and if I drop a perpendicular from the center of the sphere down to the center of the cone, I'm going to call that distance x. And then from the center of the cone to one corner of the cone, I'll call that y. And the reason why I did that is because I've created a smaller right triangle here in this picture. And I'll need to refer to that later here. But so the volume of a cone is 1/3 pi times the radius of the base squared times the height. Well, in this picture, I've got 1/3 pi times the radius of the base, that's y squared, and then times the height of the cone, that's r plus x. Okay, now I'm going to be maximizing the volume of this cone, and this is going to be a function of x. R is a fixed number, right? R is the radius. That is not changing in the problem, but x could change. If I redraw this cone several times, x would, take on many different numbers. So let's see. I don't want y involved in this. I'd like to have a function of x where I've only got x. Now, in this picture, like I said, I've got a right triangle, so I could use the Pythagorean theorem. X squared plus y squared equal r squared means that y squared is the same as r squared minus x squared. So where I see the y squared here in this formula that I'm trying to build, I'll go ahead and write it r squared minus x squared. That way everything is in terms of x. Okay, and I'm maximizing the volume as a function of x. Now, what do we know about x? Well, x can't be bigger than the radius of the sphere, right? That's not possible, since otherwise the cone would be out of the sphere. X can be a negative, okay? Just like in the last problem, x negative means that the base of the cone, in this case, would be above the center of the sphere, okay? So, I could draw a cone like that, and therefore x would be a negative. So I've got my closed interval, though. Okay, and again, that's a strategy I'm trying to go with here, trying to get a closed interval. I can't always get a closed interval, right? But that should be at least something that I'm, thinking of early on in the problem. Now, if x is r, then you would just have a single point at the top of the sphere. You're not actually building a cone, and that's okay. X could be r. That's fine. That is a possible value that, and if x is negative r, if x is r, you've got a vertical line in the sphere. You're not actually building a cone. If x is negative r, you'll have just a single point at the top of the sphere. Okay, and while those two options are not reasonable because we're trying to build a cone, it still allows us to get our closed interval here that we need. Okay, so moving forward, I'm going to be using 4.1 to find the absolute max on this closed interval. Well, I'll need to find my critical values. So let's go ahead and find v prime of x. It's going to be 1/3 pi times the quantity. All right, I'll need a product rule here. So the first is r squared minus x squared times the derivative of the second. Again, r is a fixed number here, so the derivative of r is 0, plus the derivative of x is 1. And then, so first times derivative of the second is 1, and then plus the second is r plus x times the derivative of the first, That would be 0 minus 2x. Okay, now r squared minus x squared, that's the same as r plus x times r minus x. So you're going to have an r plus x in both of these groups. Let's go ahead and factor that out. You see, you'd want to be careful about like distributing and collecting like terms. I'd like this to be in a factored form because then when I can set this equal to 0, I set the factors equal to 0. So once I've pulled out the r plus x, there's an r minus x still left in group 1, and then we've still got this minus 2x from group 2. Or r minus 3x then would be, the simplified form of the leftover. Set this equal to 0 and solve for x. R plus x equals 0 means that x equals negative r. R minus 3x equals 0. Subtract r and divide by negative 3. That means that x is r over 3. Okay, and so now I'm going to plug in my critical values. Now I would have plugged in negative r anyway, since that's an endpoint on this closed interval. It's still a critical number though. And so yeah, let's plug in r over 3, negative r, and then positive r into v, and see which one is the biggest. Well, if x is negative r, and you plug that into v, you're going to have 0. And that should make sense, right? If x is negative r, I mentioned that you're going to have just a single point at the top of the sphere. You're not actually building a cone, so the volume is 0. If x is r, and you plug that in, here's r squared minus r squared is 0. If x is r, you're going to have a vertical line in the sphere. You're not actually building a cone, and so therefore the volume would be 0. Now if x is r over 3 and you plug that into v, you're going to have pi over 3 times the quantity r squared minus r over 3 squared, that'd be r squared over 9. And then r plus r over 3, well r is the same as 3r over 3, right? So if you got 3r over 3 plus r over 3, that would be 4r over 3. R squared minus 1/9 r squared would be 8/9 r squared. And 8 times 4 is 32. I'll still have pi, and then r squared times r is r cubed. I mentioned this is 8/9 r squared, so you're going to have 9 in the denominator. Times 3 would give me 81 then in the denominator. Now r is positive, so 32 pi r cubed over 81, I know that's going to be a positive number. That is bigger than these other two. So therefore, when x is r over 3, I know for sure that this is an absolute max. This is the proof that that is correct. Okay, and yeah, so the nice thing about having this formula is because now I can say, okay, what if we wanted to find the volume of the largest circular cone that can be inscribed in a sphere of radius 4? Okay, well if r is 4, I can know what that volume of the cone would be by just plugging that into this formula here. Or if r is any positive number, I can have an immediate volume of the cone figured out then. Okay, we'll stop right here then.